Thank you, everyone. My name is Andrey Latyshev. I'm from University of Luxembourg. My supervisor is Jack Hale, and together with our colleagues from France, Jeremy Blair and Corrado Morini, we developed a very interesting tool that a lot of you will love, I hope. It's about expressing general constitutive models with algorithmic differentiation techniques in DOLFINx. And I suppose it's a logical continuation of the presentation from yesterday of Mr. David Ham about external operators. You will understand everything in a couple of minutes. So in solid mechanics, we want to solve equilibrium problem in the variation formulation 1, where the strain tensor is an explicit analytical function. Um, and if we know the analytical expression of this relation between the stress tensor and displacement field U, we can easily formulate this form in UFL and then discretize and assemble. But what happens if we don't know this explicit expression of the stress tensor? And this is a common situation in real applications where this constitutive model of this relation between sigma and u may be represented by experimental data or neural network or a numerical algorithm. All these ways to express a constitutive model we are not able to use simple mathematical functions in this scenario. So we need a kind of solution which we propose in the form of our framework that enables which allows to use any third-party libraries to define such constitutive models. And we use NumPy arrays to manage the data between the Phoenix 6 environment and external code. And the framework is based on two important concepts of external operators and automatic differentiation. And the external operators was originally introduced by Mr. Buziani and Mr. Ham. We deeply appreciate your work on this subject. Without this, this work is not possible. And I just remind you the definition of external operator. We treat it as a symbolic UFL object that can be defined by a computer program, not analytical mathematical equation. So it has a very important property of differentiability, and we treat the derivative of the external operator as another external operator. And it's quite important because typically we want to take the derivative of a nonlinear form f that may depend on this external operator n, and following the chain rule, a derivative of such an object will appear. So let's come back to solid mechanics. There we treat the sigma as an external operator that acts on the strain tensor epsilon u. And according to our framework, we diverge slightly from the original external operator concept. In our framework, we implement the FEM external operator class, which has three main fields: operand, on which the operator depends; functional space, where we evaluate values and store them of the external operator; and the Python function, where we define the behavior of the external operator. In solid mechanics, the derivative of the strain tensor of the stress tensor is a consistent tangent matrix, stiffness matrix, which, as I told before, it's another new external operator that will be automatically appeared in Jacobian after applying the symbolic automatic differentiation tools of UFL. And so how to define actually external operators? We just create two callable Python functions that receives NumPy arrays the values of evaluated operands and returns the values of evaluated external operators. Here, I just focus your attention on the fact that we escape the Phoenix 6 environment, and inside of these functions, we can use whatever we want, just that data manipulated via NumPy arrays. So uh, in total, we have external operators that depend on some UFL expressions or operands and external code. And then we, before assembling the final forms, we use NumPy arrays um, to build the bridge between the DOLFINx and external libraries. To demonstrate how our framework works, we implemented a complex plasticity model of Moore-Coulomb. Here you see the equilibrium problem 4, and with the constraint 5 on the stress tensor. And typically, to solve such system for 5, we use a certain numerical algorithm, which is called the return mapping procedure. It consists of solving the nonlinear system 9, and sometimes we can solve it analytically, but in this scenario it's not possible, and we must do it numerically. That's why we use another Newton solver, the local one. By implementation of the external operators, we mean the implementation of this return mapping procedure. And it's done via the package JAX, which provides the robust tools for automatic differentiation and just-in-time compilation. How to use automatic differentiation in solid mechanics? Actually, if you have the function that returns the values of your stress tensor at one point, at Gauss point, like the one we need to define the external operator, you must just pass through the AD tools of JAX to let this Python, this computer program be applied to this some functions of JAX, and then we receive another computer program that will compute the derivative of the stress tensor exactly at the same Gauss point. As I mentioned before, to solve such a system, we need an iterative solver, Newton solver. Regardless, we still can pass such a program that contain, for example, while loop through automatic differentiation, and we still can get a new program that will compute the derivative exactly. So all the functions before were implemented locally for one node, and then we can easily vectorize now these functions to let them pass through all Gauss points of our functional space, and then define the behavior of external operators. So before JAX, before AD, so we had to define all the derivatives manually. For instance, just to define this nonlinear system, we have a term, the derivative of the plastic potential. And before we had to derive this huge formula here manually, and where each term is quite big expression, and after all it takes like several hundreds of lines of code to implement the whole model. You can find this one here, and now we can just write one line of code in Python, and that's it, and it will be efficient, and yeah, it gives a lot of a feeling of power. So after yeah, and moreover, I just showed you one example when how we define the system itself. Then we need to differentiate the whole system locally, and then pass through the AD, the whole algorithm to get the global derivative. So, and on every step we use AD. to verify that our automatically differentiated functions are correct, we do two tests. The local one that justifies that the constitutive model restores correctly the stress tensor, and all the values remains within the plastic limit. And then for the global problem, we implemented Taylor tests, which verified that we get the correspondent convergence rates for the first two Taylor remainders, like here for the plastic phase. And for the elastic phase, well, the constant of the stress tensor, the stress tensor derivative is constant. That's why we get this convergence. So here I demonstrated just one example how this framework can be used in plasticity problems, but you can imagine how you can use it for other problems within solid mechanics, and you can use other packages. But you can think beyond even solid mechanics or even Phoenix 6, because in my opinion, I treat this as a tool letting DOLFINx to absorb all the functionality of other packages. And here we demonstrated just how we can adapt modern automatic differentiation tools within DOLFINx, and now it's a part of this um, beautiful library. So we implemented a framework that provides the user with an interface which can be used uh, to use third-party libraries to define constitutive models. In particular, we used JAX library for automatic differentiation techniques within JAX, and it's very robust and effective tools. You can use it. And yeah, to verify that performance is enough, we used just-in-time compilation techniques. So please, you can use it already. There is a repository. Do not hesitate to go there and put a star. I will be glad. And if you follow this QR code, you will find some tutorials. So in particular, you find this more Coulomb example in details. You can use it. So yeah, enjoy. Thank you.